I will try to give you an overview of what we can do with transient grating in the world of magnetism. So let me start by showing this. I don't know if all of you know that DOMO does a survey every year about, which is called Data Never Sleep, about the usage of data in our world. And last year, within 1 minute on average, we did 5.7 million Google searches. And each Google search consumes like a 60-watt bulb for 17 seconds, which means that every minute we basically consumed the same energy as keeping a light bulb on for 3 years. This is obviously a challenge for society, and it's obviously a challenge for research, because we need to find more efficient way of harvesting energy, of storing energy and data, and also of using it. And all the devices that I'm showing on this slide have something in common. They rely on functional interfaces where the energy and information transfer occurs within milli-electron volt to electron volt energy scales and on time scales on the order of femtosecond to nanosecond. And the functionality and properties of these devices is given by nothing else than the interplay between the 3 degrees of system, so charge, spin, and lattice, in a very subtle way, which involves weird transport phenomena, phase transition, collective excitations, and so on and so forth. And, well, pump probe techniques are actually the techniques that allow to selectively investigate the time evolution of these 3 degrees of freedom and how they compete with each other. And extending these techniques to the XUV gives us the possibility of having chemical specificity and also to access a larger momentum space, as Alessandra was saying this morning, or in real space, a smaller length scale. So in particular, transient grating spectroscopy, as I will show you at the end of my talk, hopefully, is or may become a tool to probe magnetic, electronic, and lattice properties in the same experiment at the same time. So what is transient grating? Well, transient grating is the easiest technique or the easiest spectroscopy you can think about when looking at third-order nonlinear optical interactions. And those are the interactions that occur in all kinds of materials independently then of their symmetry, and it's called four-wave mixing. And in the case of transient grating, what you have is you have 2 laser pulses that have the same frequency that interact on the sample, interfere, and create a standing wave. This standing wave acts as a grating for the third pulse, which is then diffracted at the Bragg angle. And if you measure the intensity of this diffracted beam as a function of time between the excitation and the probe pulse, you can basically extract information on the electronic response and on the lattice or spin response, as we will show later on. So of all the low energy excitations that you can create with the pump, that have a very peculiar characteristic. It's an optical experiment, but it's not working at k equals 0. It's an optical experiment where the excitation carries a momentum that is given by the crossing angle of the 2 pump beams and by their wavelengths. So these are optical excitations not at k equals 0. So what can we do with transient grating? Well, if this is our sample and we have these 2 electric fields interfering and there is no absorption, the first thing that happens is that you create strain. You have a field-driven excitation. And this will lead to electrostriction and the formation of elastic wave. But if you have absorption, you have an intensity excitation. And this intensity excitation, again, excites its electron. These electrons couple to phonon, polarons, magnon, excitons, whatever, or molecular vibration. But they also, coupling to phonons, induce heat. So they create a thermal grating. And again, the thermal grating will couple through elastic interactions to the magnetic system. It can couple via thermal expansion and launch elastic waves, or it can then go to structural relaxation, heat waves, and so on and so forth. Finally, you still have a parameter in your electric field you can play with, which is the polarization. And this parameter, again, leads to the formation of what's called polarization grating, which can directly drive phonons or magnons or other kind of collective excitations. So transient grating is, I want to remember this, the intensity of the transient grating is always positive, is a quadratic effect. And this is important because even if you would isolate one of these excitations, its time decay or its frequency will be double as fast, double as much, and so on and so forth. So the numbers you extract are never directly the time scales that you would think of, or the frequency that you would think of for the excitation. So what do we need in order to develop this technique in the XUV? This is the easiest possible XUV transient grating excitation pathway. So you go from the intensity grating to the thermal grating to a change in density. So your sample ends up having regions where the density is higher and regions where the density is lower. And if we would like to do some math, which I don't, in the end, it turns out that the efficiency of this transient grating is given by this change in density. And putting in the numbers, you end up having an effective efficiency of about 10 to the minus 7, 10 to the minus 9, with a pump excitation, pump flux of 10 to 100 millijoules per square centimeter. Which means that if you have 10 or 100 microjoules in your probe pulse, which turn out to be 10 to the 11, 10 to the 12 photons, you would have a reasonable signal of about 1,000 photons per shot, which is something we can detect. But we need a source that gives us these numbers. Another peculiarity is what happens at the surface of your sample. So obviously you have changes in density in the bulk, but you also have changes in density at the surface, which lead to expansions in the areas that are hot and nothing in the areas that were not pumped. So in the visible, this is not a very strong effect, but in the XUV, this becomes pretty strong, because if you put in the numbers for the transmitted and the reflected efficiency, you see that the reflected efficiency depends on the surface displacement and on the reflectivity of the sample. And you have a number which resembles pretty much what I gave you before for the transmitted signal. So transmission and reflection signal can be almost comparable. And this actually launches surface acoustic waves. So we could use XUV transient grating even to detect very short wavelengths surface excitations. And on top of that, back diffracted signal allows us, for the first time in the XUV, to measure something that it has not to be transparent or super thin, which is a very big step forwards when we want to measure magnetic systems. So we now have what we need. We need to find the source. And luckily, light sources have evolved quite a few in the last decades. So we started back here in the 60s, where we had the almost perpendicular evolution of synchrotron radiation and laser sources, with one community focusing on nonlinear optics and on coherence and on high field, and the other community focusing on core resonance, high energies or small wavelengths. But in the beginning of this century, basically, XFELs came up, and with the goal of combining these two worlds and joining these two communities. Typically, we have two kinds of FELs. So this is what almost everybody knows. A LINAC, an electron bunch, and then a row of ondulators where this electron bunch, by noise, enters this microbunching regime. And from this microbunching regime, depending on how long is your chain of ondulators, you have these very characteristic comb-like pulses that can go up to hard X-rays, are very short, femto to attoseconds. And very bright. Then there is another kind of FEL, which is a seeded FEL, where this microbunching is done in a controlled way by the interaction of the electron bunch with the seed laser in a very special ondulator, which is basically tuned to the resonance of to the frequency of this seed laser. This leads to a pulse that has almost the same coherence properties as the seed laser, which means in terms of wavelength, in terms of time duration, in terms of coherence. The emission of a seeded FEL is basically a transform-limited pulse. So we now have a transform-limited pulse in the XUV with the photon densities that we need, the photon densities that I was talking about before, so 10 to the 13 photons per pulse. And an optical jitter of below 10 femtoseconds between the FEL pulse and the photoexcitation laser. So this is Fermi in Trieste, and it's actually the only source in the world that is currently working in this seeded regime. We now have the source, we need the beamline. Sorry. The seeding allows us also to play a bit with what we get out, because we can start thinking about using two different seeds, doing weird schemes, and so on and so forth. So we have a multicolor functionality, which is very important for the transient grating experiment. And as I will show in the very end of my talk, we can also work with two different pulses emitted from the FEL that have different circular polarization at the same time. So one circular right and one circular left, which we can then combine at the end station. Source, beamline. So the transient grating beamline was built in order to fill this so-called mesoscopic gap. So there is a gap basically in the momentum energy diagram where all the available scattering techniques cannot work, which is exactly the interesting length scale for studying glasses and amorphous systems. So Timer was built in order to fill this gap, and if you put in the numbers for the possible crossing angles of the wavelengths we can have and so on and so forth, you see that we actually cover exactly this 0.03 to 2.5 inverse nanometer momentum region and frequencies that can go up to 10 terahertz. But it's not an easy beamline. So this is how the schematic of the beamline looks like. We have two geometrical beam splitters that separate the pump branch from the probe branch. And then in order to have all these possible crossing angles, we have 12 different toroidal focusing mirrors that we can swap. The probe is going through a delay line that goes up to nanoseconds, and in order to have this very long time range in the XUV, we had to work with multi-layer mirrors. So the energies of the probe are actually fixed, and this determines also somehow the photon energy of our pump pulses. And it goes down from, well, we can swap the mirrors. We now have even the 6 nanometers. It depends on the experiment you want to do, and I will show you later why it's important. So we change mirrors, we change angles, and we move the mirror to change the time delay between the two pumps and get a time overlap. So in reality, it looks like this. It's a bunch of vacuum chambers. Here you have the probe chambers. There are still 2 pump chambers missing here. It's at the beginning of the construction, and it is a huge UHV system. And here is actually where all the sample beam interactions occur. So this is a typical XUV transient grating spectrum. You see very nice oscillation. This is an acoustic phonon. And if you zoom in at the time overlap between the pump and the probe, you see almost nothing, and then the starting of this acoustic response. If you would do the same experiment probing in the visible, you would see a huge electronic signal at time 0. which you don't see if you are not working at resonance with the EUV probe. You see a very tiny electronic signal. So what we learn from here is that, in some sense, playing with resonances or not resonances, we can decide what we are probing. We can probe the lattice or the electrons, and that the core hole resonances are needed in order to exploit the electronic response. Now we can play with magnetism. We have a new system, a new setup with a specially designed electromagnet, thank you, Stefano, for very large crossing angles, and we install the mirrors to probe resonantly at the copper edge. The idea here is that you have a fully magnetized sample, and that when you come with your EUV excitation, you demagnetize the photoexcited areas and leave the other unaltered, and then you probe this magnetic grating. And over time, you probe basically the relaxation back to the fully magnetized state. And this is what you can see. So with the field off, you have the electronic resonance state, and then you have the thermoelastic response of your sample. And when you turn on the field, you have a huge magnetic response popping up. So the first electronic signal is still here, and then this is the magnetic response. And the relaxation time depends on the periodicity of the grating you are inducing. So this is what happens, what I showed you already. This is what happens when you zoom in. So you have this ultra-fast electronic response visible. And then when you change the grating periodicity, you see that for shorter periodicities, the relaxation time also becomes shorter. And this is basically an indication of transport phenomena. I mean, the dependence on the transient grating periodicity indicates transport phenomena. So, as I was trying to convince you at the beginning, we have a tool to probe magnetic, electronic, and thermoelastic dynamics in a single experiment with ultra-fast time resolution and momentum resolution. Now, we can go further. So this is what happens when you go to 17 nanometers periodicity by just simply changing from the cobalt to the gadolinium edge and reduce the period. This is not important because we just want to get to our record. We actually would love to go in the single-digit nanometer regime by going to iron and L edges of cobalt. But because we are now approaching a regime where actually what we are doing, so that the demagnetization pattern we are creating on our sample is getting on the length scales of the transversal relaxation phenomena. So we can now, as a function of transient grating periodicity, start learning something about transversal spin diffusion and transversal relaxation phenomena in this kind of ferrimagnets. Then we also want to see if we are capable of, distinguishing the two kinds of signals. So we installed also a very easy polarized system. We have another multi-layer mirror that reflects basically, our probe is vertically polarized. This reflects only horizontally polarized. So this is a way for us to distinguish between the magnetic and the overall thermoelectric signal. So you see when I switch off the field, I basically have no magnetic signal at all. And this can be rotated by 90 degrees, and then I could measure only selectively the thermoelectric part, the non-magnetic part. And again, I could differentiate all kinds of dynamics in the single experiment. Switching a bit to the physics, this was all nice, but this was all thermal. Are we able to do something directly with light? So are we able to look at the regime of all optical switching, where we are playing directly with the exchange interaction? And the answer is yes, and we can do it in the nanometer scale. So this is an experiment that combined real space microscopy experiments in the visible with the FEL transient grating experiment. And what I'm trying to tell here is that when you have all optical switching, which has a very critical fluence regime to occur, so it's a step like fluence transition, your response goes from being kind of periodic to having this regime where you switch and do not switch, which is where the line excitation ratio is not like on and off, or don't have a one-to-one ratio anymore. And this is basically reflected in the appearance of a second-order signal. And then when you go back, like when you go over this all-optical switching regime, you have, again, a one-to-one ratio. So we combined basically the optical experiments with the EUV experiments. This is the optical microscopy. And what they see in the optical is that you have this very strong regime for all optical, well, the very small regime for all optical switching. And this they could see by basically looking at the shape of fringes. And that when all optical switching occurs, the relaxation time dynamics do not follow the typical magnetic relaxation time dynamics, but the signal remains basically on for very long time scales. And if we look at our R2-to-1 ratio, so the ratio between the first and second order diffraction in the EUV, we observe a very similar thing. So even at 44 nanometers and not at 2 microns, you see the same physics. So we can actually use this 2-to-1 ratio as a signature point, and the dynamics are pretty much the same. So now we have a tool to study also all optical switching in the EUV, which is this ratio between even orders and odd orders of diffraction in the transient grating. So I only have 5 minutes, but I only have 2 slides, which are the cross-polarized experiments, the thing I was talking about before. So this is the signal I've shown you at the beginning, this cobalt gadolinium at 44 nanometers. And this is what happens when you measure the same sample in reflection. You have the signature of the surface acoustic wave. And this is what happens when you switch to this cross-polarized excitation, where the intensity at the sample remains constant, and it's the polarization that has a periodic progression. This is what we observe. So we have a rise time, which is the same as the magnetic signal, and a much faster decay time. But the question is, here is, what is driving this excitation? What is actually creating the grating if my intensity is constant? And there is no evidence of other kind of intensity-driven excitation, like, for example, surface acoustic waves. Well, another question that we have is, why is this rise time actually resembling pretty much the first decay time of time-resolved MOCA experiments? And yeah, and also we know that the relaxation time depends on the grating periodicity. So the open questions to be answered were, what is the excitation mechanism that leads to this magnetic signal? And why, at the same grating periodicity, I have such different magnetic relaxations? We did some optical experiments at the Sprint lab of the CNR with 2.5 micrometer periods, both in intensity and polarization grating configuration, on the very same sample. And well, what you see in intensity configuration is that this is the EUV data, this is the optical data. It just takes much longer to relax, which is exactly what was expected for going from 44 nanometers to 2.5. But in the polarization regime, you don't see anything at all, not for this sample. So now the question is, what was the cross-polarized excitation in the EUV? And I kind of have my theory, but I still need to find a real confirmation for it, that we are actually pumping in a dichroic wave. So right circular, left circular are pumping the spins with a different probability. And then we have different diffusions or different, yeah, minority and majority charges have different speeds. And so this is actually why we end up having a grating. This is, yeah, my first idea. I'm just putting it in the audience because I don't have any confirmation experiment yet. And with this, I just conclude, which I hope I showed you that XUV transient grating can be really used as a tool to probe several different interactions in a sample between all the different degrees of freedom. And yeah, these are just the take-home messages from the 3 different experiments I've shown you. And before I just really shut up, I want to thank everybody that is involved in this collaboration. We are a user beamline, so these are just the groups that have contributed to this very small part of the story. And you for your attention.
Thank you, Laura.